Okay, so we'll be starting our chapter. We are starting chapter 4 of your chapter book. This is very simple to be understood, but still some aspects are there that you need to know differently. Okay, is the screen is shared or not yet?
Not yet, sir.
Not yet, sir.
And today I have some issues of network or the speed. I don't know whether we would be able to complete our lecture in a repeated way or not. Okay, let's try. So you see, you can easily see that whenever we approximate a function, then in our case, we may have our differential equation, we may have our integral equation, we might have our other form of linear algebraic equation or something like this. In all the cases, we have to deploy our approximation technique there. But in our cases, okay, when we introduced some what we call intuitive aspects of numerical computation in chapter 1, we have seen that after modeling, you will find some equations. That equations are sometimes differential type say. Then what we have done there, we approximated the derivative by using some differences of your function values at 2 instance of time. Can you remember this thing in our last class? The derivative that we have approximated by using the values of the function at 2 instance of time. Can you remember this equation? Okay, yeah. Okay, we illustrated this thing for an inductive circuit. If you have a di by say dt, that di by dt can approximated by del I by del t. Okay, and if you have your current at 2 instance of time, say I plus 1 minus I divided by say del t, isn't it? Because in
Yes,
this
sir.
way we can do where del t is your step size. So now we will be, although this equation is derived from the basic definitions of slope, but you will see that this actually belongs to an approximation technique that we sometimes call Taylor series approximation. Have you heard about Taylor series earlier?
Yes, sir.
Okay, then you know this thing. The Taylor series is actually a converging mathematical series by which you can approximate a function by using the function, approximate a function at a particular point in the independent variable by using the value of the function to a point of other values of independent variable. That means if we have a function, let me show it. For example, say if we have a function fx, that fx function things are not working well. Okay, if we have a function, that function, for example, say fx, and your x is in the general case, x is an independent variable, fx is your function, that at the point xi, you have a value of your function fxi. At the point xi minus 1, you have a value of your function x minus 1. So if we consider that the value of your function at xi is known to us, we need to predict the value at xi minus xi plus 1. And these 2 points are separated by xi minus 1 plus xi, let us call it h, the step size. Then what we can do, your function may vary in this way between these 2 points. But what we can do, if your h is sufficiently small, then this point can be thought as a straight line, isn't it? If this point can be thought as a straight line, then how the value of your function at point xi plus 1 can be approximated? You know the value of this point, this is your f xi. Then you add this term there. And that adding term is coming from which perspective? If we know the slope of this curve, then we multiply the slope by h, and that is what this amount. Okay, this additional amount is equal to what? Slope of the curve multiplied by the step size, isn't it? Your slope is nothing but rate of change. Is it not rate of change?
Yes, sir.
If it is the rate of change with respect to the independent variable, and you know over which that rate of change is prevailing and it is constant, then what you can do, you can simply multiply that slope by the step size to know the contribution on fxi, so that this contribution can be added with fxi to find the value at xi. This is some sort of approximation, okay, that can be done without going to any mathematical rigor. Simple what we call logic can be applied there to approximate this value. But if you want to refine this approximation, what you need to do, you have to consider this curvature effect. That curvature effect can be considered by adding more term in it of higher derivative. If we proceed with doing this thing, you will obtain this equation 4.5. This is what the general form of what we call Taylor series. Okay, you see that in our first approximation, when this was a straight line joining from point xi to xi plus 1, this is had this approximation. Okay, here this difference I plus 1 minus xi, this difference is actually the step size h. Then if we add, for example, a second derivative term there, then again your approximation will be refined. You can add your third derivative there for further refinement. In this way, how far you can go? We can go up to a finite numbers of terms. Then we'll have, for example, a reminder there that because this is an infinite series actually, but converging. If that infinite series is converging, what does it mean? It means that the higher order terms is contributing gradually, progressively less to your approximation. As a result, after you finite numbers of terms, you can discard the higher order terms. This discard we sometimes call truncation. So you are truncating your series after finite numbers of terms. That truncation will involve some error. That error is also an important issue of numerical to examine the performance of a numerical algorithm that involves Taylor series. So your truncation error is another error. We are adding with it. Then truncation error, and in your, the earlier case, you have been introduced with roundup error. The two types of error actually occurring simultaneously in numerical computation. One is your error. Apart from the error, there exists another consequence of numerical computation, that is called stability. That stability concern is a serious issue when your algorithm involves, for example, a time particularly. We will be discussing the thing later if possible, because stability needs more mathematical rigor to be understood. But what you can say at this stage that a numerical algorithm will be stable when the error in progressively diminishes during the course of computations. If your error is, for example, increasing in each stage of your iteration, then what will happen? Your solution will be simply dissolve into the error, and you will get nothing. So this type of situation might occur in some cases. Then we'll discuss the thing. We refer to some particular issues when they will arise. So in this way, you can have your approximation by using your Taylor series, and truncation error will be there. Okay, now the thing is that how your thing will be that if you have a function, that function might have, for example, derivative exist after finite numbers of okay, derivative actually up to some finite order. But beyond this, you will not have derivative existing there. In this case, truncation can be there, but still you see that your value of your derivative will be progressively reducing if you take your higher order derivative. But some functions can be there where your derivative number is infinite. For example, if we have a function consider that if we have a function, say x square, say x cube plus 3x plus 5 equal something like this, then what will happen? How many derivatives we can obtain there? If you just take first derivative, second derivative, third derivative, then no other derivative will exist. But if we have a cosine or sine functions, it is very difficult, okay, maintaining office from the home and taking lecture. Lots of things are there, gradually getting, for example, mad. Okay, can you hear me?
Yes, sir.
Okay, so following the previous discussion, what we can say now that if we have a function, that function has derivative calculatable, then this function can be approximated with the help of Taylor series. Sometimes your function might have finite numbers of derivative. In other cases, your function might have infinite numbers of derivative. In both the cases, we can use Taylor series. So we'll be illustrating the thing by using an example, then we'll be progressing further, okay? So you see that your approximation will come gradually. For example, say if we have our first term added, then it is the zeroth order approximation. Then we can use the second term that will involve the first derivative. This is your first order approximation. And if we involve, for example, your second term derivative there, then it is your third order approximation. In this way, the order of the approximation is counted. So you reminder there will be something like this. If we have our first order, zeroth order approximation, Then the remainder is designated by R0. The R0 term will involve the first derivative up to the all higher derivative there. So in this way, if we have a function, that function can be approximated by using the value of the function in the vicinity of a point. For example, in this problem, you see you have to predict the function value at xi plus 1 is equal to 1. That means this is the next point where you need to estimate the value of your function. Now, what will be the then our value given xi? Your xi is the 0. Okay, that means if we have our function given, and the value of your function is known to you at say xi, then you have to predict the value at xi minus 1. That means these 2 points are there. This is your xi, this is your xi plus 1. Now our xi equal to 0, this is 1. So this is actually the step size. Then your h would be equal to then 1. And as your function is given to you, then your f0 is equal to 1.2. So if we have, for example, our first order approximation, then your xi plus 1 is equal to f1 in this case would be equal to say f0, and that is equal to say 1.2, the first order approximation. Then if we want to find the second zeroth order approximation, and if you want to just add another term with it, then your xi plus 1 is equal to say f1 can be written in this way, that it will be equal to f0 plus your first derivative at point xi multiplied by h. In this way you can do. How to do that? You take the first derivative of your equation, put x equal to 0 there, that will give you the value of your first derivative at x equal to 0, multiply it with h, then it will be your second derivative. Now, if we put the value x equal to 1 in this equation, you will have a true value known to you. Then these are the approximate value. So at each stage of your approximation, you can calculate the error, the true error relative or true error actual, okay? Just by differentiating the value of your function in two domains you have calculated. So if we go just on adding more terms in your approximation, you will see that your curve is gradually for example, actually this slide is by somewhere or other has some problem. No problem. Will be. Let me just edit the slide. Okay, I hope you can see it now clearly. Okay, you see that the value of your function at x equal to 0 is known to you, and you are approximating the value of your function by using Taylor series at x equal to 1. Then okay, we are here at 0th order approximation. Then if you add the first term there, then first derivative, then it is your first order. Then if you add your second term, it is your second order. Then this is the black curve is the exact, for example, value of your function. In this way, you can easily find that how in the first case of 0th approximation, this is what your error. And your second approximation, this is your error. Your third approximation, this is your error. So if we add more term, you gradually your error is decreasing and your curve is coming, moving in this direction and going closer to the actual value. In this way, you can do that. But how far we need to go, because as this function is known to you, you see that that function will have finite numbers of derivative. So you can truncate your calculation after a few numbers of terms, or you can even go up to the point where your derivative becomes zero. But we may have our situation where your derivative terms are okay, number of derivatives are important, okay, infinite. For example, this is what that problem, that we have a function that we need to approximate. That function has infinite numbers of derivatives, like cosine function, sine function will have infinite numbers of derivatives. Then how to solve whether this approximation will work there or not. Okay, this example is say cos x. The value of your function of cos x at x is equal to pi by 4 is given to you, and you have been asked to approximate the value of cosine at xi plus 1 equal to pi by 3. So then we can use our Taylor series approximation here again to predict the value of your function at xi plus 1. Okay, you can easily do that. Here, you difference of xi plus 1 minus xi will be the step size, and your step size is equal to pi by 12. So you can proceed in calculating the thing there. Okay, so for your first order approximation, you will have network is very unstable. So you see that your function value are given to you. Function value is given to you at pi by 4. And in this case, you see that as your derivative will be infinite. So in this case, actually, your prediction is needed. For example, if your value, for example, you know the value of, because this is a periodic function, if you know the value of your function between 0 to say pi by 2, then other values will be replicating, isn't it? Other values can be generated by using the values between this, if your x is between 0 to pi by 2, this is what the quarter cycle of your cosine curve, and by using that quarter cycle, other parts of the cycle can be generated easily. So you use your value, for example, that your xi value is equal to pi divided by 4, and your xi plus 1 is equal to pi by 3. Then your h is equal to pi by 3 minus pi by 4 is equal to pi by 12. Then your first order approximation is what? First order approximation is, say, cosine pi by 3 would be equal to say that is cosine pi by 4. This is your first order approximation. That means your fxi plus 1 is equal to fxi. Okay, then you calculate your error. Similarly, your second, if you add your second term, then it will be your second zeroth order, first order approximation, and that xi plus 1 would be equal to fxi plus h into f dot xi. Oh, okay. What is in your case? What is your f prime xi? Can you tell me what is your x prime xi? Your function is cosine x.
So it will be sine pi by 4.
Only sine. If you differentiate your cosine, it is sine. Is it not minus sine?
Oh,
Minus. Okay, minus pi divided by 4. Okay. So your second function would be equal to what? Then if your xi is given, this is your cos pi by 4 plus what? H equal to pi divided by 12 multiplied by minus sine pi divided by 4. So in this way, you can calculate the thing by including your first derivative. So in the same way, you can include your second derivative. That you see that your derivatives are they are always present. But at each stage of your calculation or approximation, you have to examine the error because true value of this function at x equal to pi by 3 is known to you. By using this value, you can easily calculate the percentage of true error. Then you will eventually see that as you add the number of terms, errors are gradually decreasing, and you can stop your calculation if you have your error criterion set that this amount of error is allowable for your approximation. Okay, this thing is described there. You see that in this table, all these calculations are summarized. If we go to the zeroth order approximation, then the value of your function is approximated from the previous value. So error ET become minus 41.4%. Then if we add another term, that means first derivative is there, that is minus sin x. Then your value is 0.0521. And you see that you, after adding a single term there, your error is reduced to minus 4.4%. Then if we add the third derivative, second derivative there, that means you are adding the third term, then you see that your value of error is now 0.449%. And you can easily see that your error is gradually decreasing. And if we add 6 terms there, then you see that your error is almost going to 0, and your value of your function is approaching the true value. You know that your true value of cos pi by 3 equal to what? It is 0.5, isn't it? Now, the geometrical, although the thing is very simple, you can also move by your own. But you can see that by using some geometrical interpretation, you can also estimate the error of your Taylor approximation. Okay, this black curve is your true curve. Okay. There exists a theorem in your algebra that is called mean value theorem. Probably you have heard it in your earlier level of mathematics. That if a function is continuous and the derivatives are also continuous between two between two ranges of your independent variable, then you may have a point between these two values of independent variable where you can calculate the slope, and that slope can be used to approximate this function. So in this way, you see, if we have, for example, a original, your black line is the original curve. Your black line is your original function, and the value of your function, for example, is given at this point at xi, and you are approximating the value of your function at this point. Now you see that if we go to the zeroth order approximation, then this is what that point, okay, where you are approximating that the value of your function at xi plus 1 is equal to the value of your function at xi. This is zeroth order approximation. In this case, this is then this must be the remainder then, and this R0 is your zeroth order remainder. So then by using, for example, slope of this curve, we can easily calculate that your remainder will be equal to this. Now, by using the mean value theorem, if we have a point xi that is between xi and xi, where the point is there on the curve, and if we calculate the slope at this point and this point are same, then these two straight lines are parallel. So what you can do, this slope h0 divided by xi can again be replaced by the derivative of your curve at the point x equal to xi. Then in this way, we can derive this equation for our first order case, and we can logically extend it for your the zeroth order case, and we can extend it for your first order case. So these things are there in your book also. You try to just have a look there, because we have to finish this thing this day. Otherwise, will not be already. We have our 2 weeks gone. We have to start our original numerical tuning there. Okay, but some other issues are there. You will see that sometimes you may have your function that is very nonlinear. If your function is very nonlinear, then a step size is another issue to be considered. Because you see that in your communication engineering, I hope you have heard about sampling of a function. Have not you heard about sampling? In your communication engineering one?
Yes, sir.
Can you tell me that perspective of sampling where you have studied it in modulation or something like this? For example, in PCM, pulse coded modulation, where you need, if you have a function given, you have to sample it, then truncate it, then quantize it, then you have to code it, isn't it?
Yes, sir.
In this case, you see that if your signal is varying very rapidly, and you are maintaining, for example, if your signal is something like that, in some region your signal is varying slowly, in others region your signal is varying very fastly, then if you want to sample the signal, that means you need to take the representative value of your signal to process, then how to find that, what will be the sampling rate? How you determine the sampling rate of a function? So if you silence is your answer, then how can I understand you? So the thing is that if you have a function, say fx is equal to x to the power m, so you can easily see that depending on the index m, the linearity of a function will be depending. For example, for m equal to 1, it is simply a straight line. Then if m equal to 2, it is a parabolic line. For m equal to 0, it is a third degree line. It's the fourth degree line, something like that. If this is the case, then if you want to approximate the function by using our Taylor series, in this example, just effect of what we call step size is studied with the considering the nonlinearity of your function. Only first order approximation had been used. In this case, you see that if we have our first order approximation, why your notation is not coming? Then this will be our first order approximation, isn't it? Because you are considering, can you tell me, is it okay or not? Because this general equation should be xi plus 1 is equal to fxi plus h into f prime xi. So here your fx is equal to x to the power m. So f prime x would be equal to m into x to the power m minus 1, isn't it? So this is what that first order reminder values are this. Okay. Now if your m equal to 1, and we are considering that our stress size is equal to 1, then you can easily calculate that fx is equal to x, f prime x is equal to 1, then double derivative will be equal to 0. So only your first approximation is, for example, first order approximation is enough to calculate the value of your function. And your remainder would be equal to 0. That means your prediction will be accurate. So your prediction is this, okay? If you want to find the value at x equal to 2, then x2 value is equal to 2, and it is easily understandable that it is accurate because no remainder is there. But if we change the value of m to 2, then what will happen? If we change the value of 2, you can easily, for example, do this thing without any lecture, okay? Because this is very simple. You need only your intermediate level knowledge, nothing more than this. If we have our m equal to 2, then your function is x square, then your first order approximation will be equal to what? Fx, f2 is equal to f1 plus 2 into x to the power 2 minus 1 multiplied by s, this is your 3. Now you have to calculate your remainder R1. You see that R1 will involve two derivatives. One is the second derivative, another is your third derivative. Your second derivative will exist, but third derivative will be equal to 0. So your remainder term will be equal to 1. So in this approximation, you see that you are having a truncation error equal to 1 in terms of absolute error, but you can easily calculate the percentage. Similarly, for m equal to 3, your function is this, that if we use that first approximation, your function value would be equal to 4. Then your remainder term will be equal to what? You will have your remainder term that will involve 2, 3, 4 derivative. So as a result, you see that your remainder term will have this value, and it is equal to 4. You see that as your nonlinearity is increasing gradually, the remainder term is also increasing. And if we want to find a general behavior for m equal to 4, you will see that the value of your function f2, this should be f2, would be equal to 1 plus 4s. And in the case of what we call your remainder term would be equal to this, because as your function is x to the power 4, okay, then after 4, no, after, okay, just this is your what we call fourth derivative. No fifth derivative will be existing. So in your remainder term, you will have this general term. Okay, that remainder is the now expressed as a function of h. Then if we set h equal to 1, then you can easily calculate what is your remainder values. But if we want to consider that we want to investigate that for this simple problem, what will be the effect of h on R, then what you can do, you can change the value of your h, the step size, and calculate the remainder. And that will tell us how your remainder is being affected by the step size. And you will see that your step size will have profound effect on that remainder value, as is shown in your next slide. Okay, just look at it. Okay, if we calculate the value of h, this is the assumed value of h, and this is the true value of your function, and your order of approximations are there. Because the order of approximation, first order, your true value is there, error, you can easily calculate the remainder, your remainder function is there. Okay, so for a particular value of h equal to 1, your true value is 16, your first order approximation is 5 for this function, and you have your remainder equal to 11. And if we half our step size, then your true value equal to this, then your approximate value would be equal to this. This is a remainder. In this way, if we keep going calculating the thing and plotting it, you see that your h is ranging from 1 to say 0.01. If it is ranging from 1 to 0.01, and your remainder value is also changing from say 10 to say 0.001 or something like this. If we want to plot these two variable if you plot this plot the curve, say h versus r, 1. Okay, is your linear plot is good? You understand my question?
Can you repeat, sir?
For example, we want to plot h versus r1. and your H is ranging from 1 to say 0.01, and your R is also ranging from 11 to 0.001, for example. Can we plot this thing in a linear graph?
Yes, sir.
Or would it be easy to do that? Then what will happen? If you have a function value ranging from a very large value to a very small value, actually the linear graph is not very convenient. For this reason, what you need to do, you have to use some logarithmic paper, okay? Have not you used this thing earlier in your courses, semi-log paper or log paper to plot, for example, the frequency response of your amplifier or some other issues where things involve from very small value to higher value. Okay, so your log paper is needed for this type of, because both values are ranging from a very small value to a high value. So we can easily plot this thing in a log paper. If we plot the thing in a log paper, then you will see that this is what your actual plot. And if we approximate the plot with a slope equal to 2 in the logarithmic curve, then the gray straight line is that straight line. In the logarithmic slope is 2, then actual thing will be equal to what? Actual thing would be equal to that your R is decreasing with h square. So if your R is decreasing with h square, what does it mean? It means that your Taylor series is converging, or the remainder is converging with the rate equal to the square rate. Okay? That means if we double our size, step size, it will cause error 4 times error. Similarly, if we have our make our step size half, then error will be reduced by a quadratic factor. Okay, that means 1/4. You can easily imagine this thing. Yeah, so your nonlinearity actually depending on the nonlinearity of your function, we can select our step size smaller so that the error will be smaller. But how small the step size can be, this is another issue. We'll be discussing the thing later. That we have our two types of error. One error will be due to the truncation, and that is affected by the step size. And another error is there that is called roundup error. That error is affected by the computational capability or rounding up of your result in the computational machine. These two error actually are opposite in nature. Let us see. Okay, some other things are there. 4.13. I am leaving the thing to you to be done by yourself. Okay, you can do that very easily. Let me just share some the textbook so that you can find some other descriptions there regarding further explanation of this thing. I hope you can understand it easily by your own. Okay, then we have our two types of error. The total error will have this nature. Okay, can you see this figure?
Yes, sir.
Actually, network problem is very disturbing because everybody is using network online. So your bandwidth crisis is there. So you see that if we have our step size, and we know that if we increase our step size, then what will happen? Your truncation error will increase. Because you see that in your last example, your truncation error is actually related to h square. So your truncation error will be increasing. Similarly, this is a log plot for this region things are straight line. And your truncation error will be decreasing for decreasing step size. But you see that when your step size is very small, we'll see in many problems your step size can be in the order of micron or something like this. In that case, what will happen when this small number is being dealt with computer, then it will again cause some rounding up error. That your rounding up error, for example, will increase if the step size is very small. So your rounding up error is something like this. Okay, If we increase the step size values, the rounding up error will decrease. So these two errors are in opposite in nature. If we just add them together, then you will have this curve. Okay, that means this is you can easily plot this error curve by using your step size. For example, say if we have a function e to the power x, you can easily exercise it. If we have a function e to the power x, then that e to the power x values can be calculated for a particular point by using your simple, okay, or we can calculate the derivative of this point. Okay, can we, if you someone will tell you that calculate the derivative of e to the power x, then how can we do that? It is simply d dt d dx e to the power x is equal to e to the power x, isn't it? So this is the value at a particular value of x, say x equal to 0.2. You have been asked to calculate the derivative. Your derivative will also be equal to the value of your function e to the power x2, isn't it? Okay, but if someone will tell you to calculate the derivative by using approximation, then you have to calculate the value of your function, say at a particular point, say your step size is equal to, say, your step size is equal to, say, 0.1. Then how can you do that? You apply your numerical algorithm there, then you can calculate the value of your function at, say, 0.2 plus 0.1 minus e to the power minus 0.2 plus 0.2 divided by your step size is equal to, say, 0.1. In this way, you can calculate your the value of your derivative at this point. In this way, you can change the value of your age, calculate the derivative, and compare it with your exponential function. Then you can plot the error that you are obtaining for each value of age. Then you will see that that will follow this type of curve. Okay, I am leaving the thing to you just to explore that what will be the error curve of calculating the derivative of the function exponential function e to the power x by varying the step size. And that will need, for example, your what we call calculating the derivative by using finite differences. Although numerical differentiation, we will deal with numerical differentiation later. But this numerical differentiation have been discussed here in your this chapter. You can easily have a look. This is not very difficult to be understood. You can have a look. Okay, you will see that if you have an error curve, by from that error curve, we can easily calculate the optimum value of your step size. That optimum value will be equal to this given by equation 4.31. So with this thing, you have some examples there. Try to redo the examples. Some programs are also there. I know you know how to write the program. You can rekey it in your computer and try to investigate it. Okay. In a particular example, you see that that error curve has been calculated by using the different values of your step size, and you see that that error curve follows the nature that has been predicted theoretically earlier. You can easily verify this thing. So with this thing, I am concluding my lecture today. Then we will be going to our next original numerical method lecture from the next class, inshallah. But I have some instructions posted in the in WhatsApp group. I am repeatedly telling you that we will be using IUT LMS for our test and other exams. But only few students accessed it, but the others are remaining silent. So look, if you cannot access your IUT LMS, without IUT LMS, I will not take any exam using Google Form or something like this. So be careful about that. But okay, I have given a task just to verify your email ID, your name, and your ID. Okay, because the list that you have supplied to me is very confusing. I cannot understand that. Particularly, the older students has some problem. It is very difficult for me to just sort them out. So I have already assigned this thing there in your LMS. You log into the LMS and answer 3 questions there. Your email ID, your name, and your student ID. And I need this thing by Saturday. That's it.